Okay, today we're going to look at assignment 3 and assignment 4, and also talk about the well, quiz 3. There's nothing to talk about. Quiz 3 will look like assignment 3 and 4, and that quiz is coming up this Wednesday. So let's just dig into assignment 3. And the first problem is to implement this function called same length, and it returns a bool. So we call it a predicate function because it returns a bool, yes or no. All right, so the predicate is like a statement. You know, A is the same as B. Is that true or is that false? All right, so let's we can do this either. We could pretend like we're in the quiz and just write it out without running it, compiling it and running it, or else we can compile and run. Which way do you want to do it? Just write it out? Okay. Here we go. So what I'll do here is basically write out what you'll write out in the quiz. So we have two vectors, A and B. And notice that, oh, it's a reference. Okay. Because it's a reference, that means it doesn't actually affect this problem at all. It just makes the code run faster or consume less memory. That means we pass a reference to A and B rather than passing a copy. So if we omit the ampersand, it means make a copy of A and B and then operate on the copy. Here we're going to operate on the original vectors. And basically we want to return true if A dot size equals B dot size. So we could do it like this. If A dot size equals B dot size, then return true. Else return false. Is that okay? Now the other way to do it, which is the way that I was just about to do, but maybe it's not clear for you, this is how I would do it. You see, this, we have these. If you look at this statement, you'll see these operations. You have to return something. Well, and then you have to compare something. What are we going to do first? Return a result or do the comparison first? Well, we're going to do the comparison first. Okay. So you can, mentally put this sub-expression inside parentheses and say, all right, that's the thing that we're returning. Well, that's a comparison. Comparisons evaluate to true or false. So if that evaluates to true, we're returning true. If it evaluates to false, we're returning false. That's what we want. So this is a more compact way of expressing this logic here. All right, let's do exercise 2. And we're getting two vectors A and B. And we want, oh, I forgot to write the test code. Let's put in test code for this. before we move forward. All right, so this is the function. And here's the test code. Now on the quiz, these will be two separate questions. Question 1, implement the function. Question 2, for the previous question, provide the test code for your implementation. And you know, your test code is sitting in a main, but you know, I don't want to see the main. I don't need to see that. Just the lines. So when we write the test code, we're going to need example vectors to pass in to the function. So let's go ahead and make those. In fact, let's call that A1 there. A1 and B1. And then we'll take A1 and push back. So you have to remember pushback. That's a function. You need to remember that function. Pushback. If you forget that function in the quiz, come up and say, what's that function again, where you add something to the end of the vector? And I'll tell you pushback, okay? You can ask me that in the quiz. I'll announce it to everybody in the class if you can't remember the word pushback. All right. So let's push back, say, like a 9 here. And that's good enough for a test. Here we've got, you know, it's kind of like a boundary case. We've got A1, it's an empty vector. We want to see if it has a different size than B1, which is a vector with one element. So there's one test. And let's test both situations. Let's do another test. Let's take the B1 and push back, say, 8. Now the two vectors have the same length. They don't have the same values, but they have the same length. And that's good enough right there for me. You're testing both cases. In one case it returns a true, in the other case it returns a false. That's good right there. Any questions? All right, let's do the next one. Is identical. Now to be identical, they have to have exactly the same elements in the same order. So if A dot, so to do the test, well, let me do this first. Well, the first thing, what we'll do is we're going to loop through. We're going to take an index I, we're going to range it through the indices of A and pull out every value that's in A and compare it to the corresponding value in B. All right, let's do it like this. So there we have it. So if A of I is B of I, and I'm showing you actually the reasoning process, the steps that many of you go through in reasoning about this problem. That you want to make sure that A of I is B of I. You can get that far, right? But here, and you write it out, you kind of get stuck here. What's wrong with this code? It only checks the first. Well, actually, if the first element in A and B are the same, we're going to conclude that we're going to return true for the whole function without checking the other elements. So in fact, if A and B, if the first value of A and B are different, we're going to continue with the loop. We're going to get exactly the opposite result. So we want to be able to go through this loop here. So this would be the reverse logic. The logic that we need looks like this. So if A and B are different, then the entire vector, well, the whole vector taken together is not identical to the other one. See, if you see that A equals B for a given I, you can't make any conclusion. But if you see that A and B are different for some I, you can conclude in that moment that the two vectors are not identical. So you need to complete this loop. You have to look at every I, where I ranges from 0 to the last index of A and B. And if you don't end up returning false, that means you've looked at every possible pair. You haven't returned false. Every pair must be equal. So at that point, outside of the loop, after the loop is finished, you can return true. But there's still something wrong with this function. You know, what happens? Let's look at a test case that makes that fail. Let's do that right now. So we have a vector of int, call it A. And a vector of int, call it B. And let's push on to A the value 0. Let's push on to A again the value 3. Let's do the same thing for B. So that test is okay. Right? That logic will work. Let's pop that open. If you walk through that, you'll see that I ranges from 0 to 1. And then we're going to look at A of 0, compare it to B of 0. They will be the same, and so this will be false. We don't return false, and so we end up returning true. So that's good right there. But what happens if we do the following? Let's suppose we push back another value onto B, say 11. And in this case, A and B are going to be different. They won't be identical because B has one more element. But this function is identical. Will return true. And so the test will fail because we negate the true value, we get false. Do you see why it returns true? Because B, we're looking at A dot size. A only has 2 elements. Now B has 3 elements. So this loop is not sufficient. We need to check, for this logic to work, we have to check that the two vectors have the same size. Actually, we need to check to see if they don't have the same size. Once again, we have to think in terms of negatives. Because if A and B have the same size, we can't make any conclusion about whether they're identical. We can only conclude they have the same size. So we need to look at the condition that they don't have the same size. If they don't have the same size, we can make a conclusion. At this point, we know They're not identical, let's return false. So now that additional piece of logic will make this second test work correctly. Now we want to have another test. We're not testing all the cases we need to test here. So we're executing this code in our second test. That's good. And we're executing this code and reaching true. That's good. But we haven't actually written any test code that reaches this point. And so that means our tests don't have good coverage, because there is a piece of logic here, or there's a statement that's not being executed in any of our tests. We execute this conditional here, that runs, but we never reach this point. We return false up here, but we never return false here. And so we say that the test doesn't have good coverage. It's not executing every statement. Also, a part of good coverage is test the boundary cases. You know, A is empty. The first test covers that. A is, actually, we haven't tested that, but we could put in a boundary case as well. So let's do this. Let's put onto A 11. So now A and B are identical. Did we reach this point? No, we didn't reach that point. I'll put in a 12 here. There we go. So now this test here, A and B have the same length. Let's see. At this point, B is 0, 3, 11. And here, A is 0, 3, and 12. And so is identical should return false. And it does that when it gets to the third element, which is I equals 2. So when I equals 2, A of I, or A of 2, will be 12, and B of 2 will be 11. So those are different, so we return false. So here we're reaching this point in our code. So this test increases the coverage of our tests. Now that's pretty good for the quiz answer. But if you wanted to go a little bit farther, you could look at some of the boundary cases, which would be, let's create new vectors, call them A2 and B2, and these should be identical. These are two empty vectors. And if we add an element to B2, well, that's not right. Now they should be false. And for the purpose of the quiz, I'm okay if the above is good enough. But down here, it just goes a little farther. It just does some testing of the boundary case. The boundary case is like a special case, like A is empty, or one of A or B is empty. And normally you don't pass in an empty vector when you call a function, right? But sometimes it might happen. So that's called a boundary case. And but up here, my concern up here is that we test every piece of code that's provided in the implementation. Any questions? Yeah.
How did you set the precondition for the same size? Did you just do an A dot size and B dot size?
Yeah, it's up here. Look, right there. We test this. So it's actually not a precondition. They can be different. A precondition means I'm not going to function correctly if you call me with violating the precondition. We don't have that precondition here. If we allow different size vectors to be passed in, we simply return false in that case. Any other questions? Okay, let's go forward then. All right, is non-decreasing. So non-decreasing, this here is not non-decreasing. You see, 3, 4, 6, that's good, but then it drops to 2. Oh, it's not. It's decreasing now. And but this is non-decreasing. We could say, I like to use the term, just I think mentally, because non-decreasing is a little confusing. If I could say weakly increasing. It's weakly increasing because, going from 4 to 4 is okay. It's not decreasing. So it's non-decreasing, and I'll say weakly increasing. So 3, 4, 4, 6, 8. That's weakly increasing. All right, so we're going to pass in a vector v into this function is non-decreasing, and we'll return true if the values in v are in fact in non-decreasing order. So, we're going to need to look at adjacent pairs of values in v. So we'll need a loop for that. And I'm just going to hammer it out from my intuition. Not hammer it out, but I'll take my first swing from my intuition. And I'll just start at 0 and I'll go to size. I know that's not right. I'm off by 1 here, but we'll fix that when we look at the statement that we need to execute. So if now we have to compare adjacent values. So the thing that's at I, we want to compare with I minus 1, or we'll compare the element that's at I with the element at I plus 1. We can go either way. Let's go this way. Let's compare the element at I with the element that comes after I. And I'm doing this incorrectly on purpose, just to show you how we get there one step at a time, making adjustments as we clarify our logic and reasoning. We're comparing the element at I with the element of I plus 1. And if there's a problem, we want to return false, that nope, it's not decreasing. So actually, we don't. It's not equality here. It's going to be that. Let's see. It's a weakly increasing. So if it's a decreasing, if the thing that comes afterwards is strictly less than the thing before it, then we're decreasing. So let's return false. Is that okay? But now there's that 1 by off problem, okay? What's the problem is the index we got to check, should we start at 0? And should we stop at a dot size minus 1? Remember, it's I here is strictly less than a dot size, so it means we let I get to size minus 1, but we don't let it get all the way up to size, right? So if v, let's take an example here. Actually, let's write the test code. 34468. Let's push back. So it's a non-decrease. I guess you have to translate that into weekly increasing. I know that it's confusing to me, non-decreasing. That's a confusing term to me. So minus 3, I say 0. Well, no. Let's push back minus 3. Oh, wait, let's use the example. Let's use the example here. So it's 34468. So 3, 4, 4, 6, and 8. There we go. So this is good. This is non-decreasing. So if we pass that in, it should return true because it's non-decreasing. So look, in this particular test, I ranges from 0 to what? Well, a dot size, it reaches a dot size minus 1. Let's see, a dot size, there's 5 elements, so a dot size is 5. So 5 minus 1 is 4. So in this loop, for this particular example, I ranges from 0 to 4. So on the very end here, we're going to be comparing, when I hits 4, we're going to compare V of 4 with V of 5. Do you see that? Is that a problem? Yeah. V of 5 is not defined because there's only 5 elements in V. That means the index goes from 0 to 4. So we're going one too far. So we need to make an adjustment. We can't go all the way to the end. Remember, we're looking at pairs. That's why we're 1 off, because we're looking at pairs. We're looking at wherever I is, we're looking to the next I plus 1. So we want to make sure we don't go off the end of the vector. And, you know, we never return true. We need to return true here. Outside of the loop, after we've looked at every pair, we need another test. Let's do this. Let's push back 7. Now, at the very last moment, V is decreasing. And so this should be false. So that's good for me on the test, if you can do that. You test all pieces of code. So in this last test here, we're hitting this line. And in this first test, we're hitting this line. And we always run this, we always run this. Now if you want to go a little farther and put the boundary cases in there, that's good. Pass in a vector of size 0. What happens when you pass in a vector of size 0? No, because look, if we pass in V of size 0, oh, this is A dot size. This should be V dot size. Sorry. V dot size. If we pass in a V of size 0, this will be 0. And that means this whole expression becomes minus 1. And but 1 is starting at 0. So 0 is not less than minus 1. So we never enter the loop. So when v is size 0, we never reach this. So we'll never have the chance to return false. So we just pass over the loop and we end up returning true. So is an empty list non-decreasing? I think in math you would say what? Any mathematicians? Is an empty list non-decreasing? What would be the mathematical answer to that? I think by convention the mathematicians would say yes. Right? Maybe it's not convention. Is an empty list non-decreasing? Is that meaningful? It's not a math class. I'm going to move on. All right, but if some of you math people think about that, and let me know your answer to that, okay? That's good. All right, let's look at this one, add 3. Suppose that array A has rows, and columns, where rows and calls are some constants. And implement the function add 3 that uses a loop nested inside another loop to add the value 3 to each element of the array. So, you know, we have this list of topics and skills that we have to cover in the class. And one of them is to know how to work with two-dimensional arrays. And the other one is to work with nested loops. So this problem basically covers that particular skill that you need to have developed at least a rudimentary level. And notice here I dropped the test code for that. The test code is too messy, and I don't want to require that for the quiz. I dropped that. So now A, by the way, when A gets passed in like this, it's in fact a reference. Well, arrays are references or pointers. And so we don't pass in A as a reference. And we end up modifying the two-dimensional array that gets passed into us. So you can look at this as when you see an array expression like this, you can assume it's being operated on as a reference. So we need a loop within a loop. So it's going to look something like this. We don't need anything here. So we'll need to look at something like this. We just have to set I and j to what we need. So this is an individual element. You can think of it as a matrix of values or table of values. You've got, you know, row I and column j, and for the slot that's at row I, column j, like a spreadsheet, we just want to add 3 to that value that's stored in that slot. So we use a for loop for that. And we do the same thing for the columns. But we're using j here. and also its columns. That's it. So there's the syntax for referring to an element in a table, a spreadsheet, an array. Think of it. This is the abstract notion of a table. Two-dimensional array. If this is confusing, here's another way to do it. You can use the word row here. And then maybe the word column here, or call. Maybe that makes it more readable. I don't know. Yeah.
What about position 1, 1, for example? Doesn't it add 3 to both? 3 to it twice? Because it covers, contains both row 1 and column. You know what I mean?
Yeah. Yeah, it's good. Now, the thing is this. When you hit, let's suppose that A looks like the following. That A looks something like this. Maybe there's a 2 here and a -1 there, and a 4 there and a 6 there. All right, that's the table. This is 2 by 2, right? So you're saying 1, comma 1, right? So this would be the element in 1, comma 1. So doesn't this logic end up adding 3 to that element twice because of the way we did the loops? Well, let's go through and think through that. We've got a row number and we've got a column number. These are going to be initialized to 0. Well, let's do it. We haven't done anything with column yet. Let's hit this point. The function runs with this value for A. And let's hit the first loop here. So at this point, we've got this variable row. We initialize it to 0. So there it is. It's initialized to 0. And then we check the loop condition, right? After we do the initialization, we don't enter the loop until we check the loop condition. And here, and I should mention that rows will be 2 and calls will be 2 in this case. All right? So A is 2 by 2. So we check the loop condition. Row is 0 and 0 is less than 2. So the loop condition is good. Now we don't do this yet. We wait till we get to the bottom of the loop and then we do the end of loop operation. All right, now the next thing we do, we're inside this outer loop. We'll hit the inner loop here. And here we define a variable called col for column, and we initialize it to 0. And we got to check the loop condition. That's what we do when we start a loop. So is 0 less than 2? The calls is 2. Yeah, 0 is less than 2, so we're good. And we don't do this yet. We do that at the bottom of the loop. So let's run this. Let's see. Row is 0. We have our record of what row and column are. So that's 0 and 0. So whatever is at A00, 0, which is right there, we need to add 3. And make that 5. All right, now we're at the bottom of the inner loop. So we execute this end of loop operation by incrementing call. So now call becomes 1. All right, that's what we do at the end of the loop. Now we'll return to the top of the loop and check. We don't do initialization again, so we can just sort of forget about that. But we have to check the loop condition. And is call less than calls? Well, column is 1 and calls is 2. All right, so in other words, the column index is still valid. So that's true. That means we're going to run this again. And notice we haven't returned up to the outer loop. We're just running inside the inner loop right now. So row has been set. We haven't touched that. So now row is still 0, but column is now 1. So the position 0, 1, which is right there, we want to add 3 to that. All right, so that becomes 2. All right, now we're at the bottom of the loop. So we modified this, by the way, modified that. We went across the columns. Now we're at the bottom of the loop. We're going to increment column. So column becomes 2. We increment the column. Remember, we do that here at the bottom. We increment column. Column is now 2. Now we check the loop condition. 2 is less than 2. No, that's wrong, because it's less than. Strict inequality. So the loop condition is false. That means we're done with this loop. We're finished with the loop. I'm going to go to the next statement. Actually, it's not really a statement. It's we hit the bottom of the outer loop. Well, now we're at the bottom of the outer loop. Oh, that means we need to execute the end of loop operation, which is to increment row. Let's do that. We go from 0 to 1. Now remember, once again, we're at the bottom of the outer loop. We just incremented row. We did the end of row operation. Now we need to evaluate the loop condition. So row is 1 and rows is 2. Yep, the loop condition is good. That means we're going to do the body, we're going to do a pass through the body of the loop, which is another loop. So what do? We're re-entering the inner loop. So that means we're going to re-execute the initialization section of the loop, because we're re-entering it. Is that clear? So column is set to 0. After the initialization, we check the loop condition. And 0 is less than 2, that's good. So the loop condition is good. We're going to do this. So A of row used to be 0, for this inner loop. The last time we entered the inner loop, row was 0, but now row is 1. And we're going to run through the inner loop with row being 1 until we pass out of the inner loop. So row is always going to be 1 on the inner loop. But column is going to range, it's going to start at 0, then it's going to go to 1, and it's going to hit 2. When it hits 2, the loop condition is false, so we don't do this anymore. So we're going to start with, am I going too fast there? So we're going to add 3 to this, that's going to be 7. Then we're going to increment column to 1. And then we're going to add 3 to, the element at 1, 1. That's 9. And then after we do that, we're going to increment column. That's going to hit 2. Then the loop condition is false, and we exit this inner loop. So we're going to hit the bottom of the outer loop. What do we do at the bottom of the outer loop? We execute its end of loop instruction, just to increment rows. So a row. Row is now 2. We check the loop condition. Well, 2 less than 2, that's false. So we exit this loop. Oh, that means we're at the end of the function. So we exit the function. And this is the result. We just added 3 to everything. So we didn't mistakenly add 3 more than once to any element. How's that? Okay, everyone? All right, there we go. All right, what about this one here? And we pass in a V and random fill. So it fills the vector V with 100 distinct random numbers. And look at this assumption here. Assume V is empty when the function is called. Assume V is empty. So that is the precondition. So if someone passes in a non-empty V, we're not guaranteed to run correctly because we have a precondition. That's what a precondition means. Let's go ahead and express the precondition. Actually, you don't have to do this for the quiz, but if you did, that would be great. I would love to see it in the quiz, but it's not required. Here we're expressing the precondition. Did I ask to express the precondition with an assert statement? Maybe on the quiz I could say, express the precondition with an assert statement. But that's how we would express the, oh, yeah, that's right. That's the precondition. It's an empty vector. That means the size is 0. Let's fill the vector with 100 random numbers. And they're distinct. Oh, there's the problem. 100 distinct random numbers. That means a given number can appear at most once in V. Let's start by doing this, the simple solution first. So we want to run the loop 100 times. The hard part about this problem is that the random numbers need to be distinct. Here we generate a random number, we put it in I. Well, we want to guarantee that every number that's in I doesn't reappear. Actually, the odds of reappearing is going to be really small. It's kind of an artificial problem here. But all right, after we insert the value, then well, let's see. Let's do it like this. See, after we insert the value, or before we insert the value, we want to check to see if that value already appears in the vector. So let's generate that value like this. N is rand. And then if n is not in V, then we'll put it in V. Oh, wait a minute. V is empty, right? So we want to push it. So we have to check to see if n, we need to figure out how do we do this test that n is not yet in V. How do we do this? Well, I'm trying to get there with pseudocode. Let's what we need to do that test is we have to loop through the existing values in V and to see if we find n there. So let's do that. So let's use K. So if v of k is in there, I mean if v of k is n, then we know that n is in the vector. So n is a bad number. And when we get to the end of this loop, we know that n is a good number. And then we'll push n onto the vector. Something like that. We're just getting there one step at a time. Just trying to craft it one step at a time. So we generate this n, and then we want to see that, we want to make sure that n doesn't appear in the vector as we have it composed to this point. So we write this loop that ranges an index k through all the indices that are in V. And for each index k in V, we check to see if n is in that slot k. If it is in that slot, then it's not good. We can't use that n. We got to have a new one. But if we look at the entire vector as it's currently constructed, and we didn't find a match for n, then we know that n is a good number. We'll push it on there. So we could do something like this. There's many different ways of doing this. Let's assume that that n is good. And if we find n in there, we'll make a note that n is not good anymore. So that when we get to this point, before we push n, we want to make sure that our record of whether n is good or not is says that n is good. We could do it like that. That's one way to do it. Does that make sense? This is still a mistake up here, okay? So there's a problem with that. We're not at the end of the problem. But just this piece of code in here, does this reliably add a new random value to the vector at whatever state it's currently in, so that we're not adding the same value? Well, I think that works. Let's suppose that works. So this code here reliably adds a new n, or it does nothing. The problem is when it doesn't add n, this outer loop is increasing I. So we're going to end up with 99 elements in V. So that means the for loop doesn't work here. We need a while loop. And it's pretty simple if you make it a while loop. Well, v.size is less than 100. We want to repeat this logic. That's it. We're going to try to get to this point to add an n, and as soon as we add 100 of them, we're done, and the loop is finished. There's other ways of expressing this logic. This is just one way to do it. And you can experiment with other ways. You can use a continue statement. That's what I tend to use. Okay, no test code with this one. This is a hard one. I know this is a tough one, right? This one's tough to understand. Okay. So we got through 5 exercises. And there's an assignment 4, and assignment 4 is it due tonight? On the 14th, right? It's due on the day of the quiz. So this is more practice for you. And you know, a pen vector. This one is pretty straightforward. Count occurrences. This is also a very good problem to work on. That's easy. Is strictly increasing. Well, that's similar to the one that we looked at already, right? So and I highly recommend you do this, all of these, of course. I mean, it's required. Is all zeros. Once again, this is that similar to the other problem we just looked at, where we have a loop within a loop, a nested loop. And it looks at every value in A and checks to make sure it's a 0. If it's a not 0, then you return false. This is what a declaration of rows and columns might look like typically. They use this keyword const. You don't need test code for that, but test code for this is good. We have time for one more of these. Do you want me to do, which one of these do you want to look at? Pen vector, count occurrences. I don't think we should look at that one. It's almost identical to the other one. Count. Here, look at this problem. You pass in a V of a vector of integers, and you pass in a given integer. And how many times does K appear in V? 0 up to size V, V dot size. Here, this one, a pen vector, we pass in a vector V and a vector W, and we concatenate the 2 vectors together. Actually, we add everything to V. So we take V and we add every element that's in W and append it onto the back of V. So I think that's a pretty straightforward problem. We're going to call pushback on V for every element in W. So if V is this and W is this, V is 425, W is 11.3, then the result is that V becomes 425, 11.3. You're just going to call it pushback. We're okay. Does anybody want to see these coded out? We have like 5 minutes left here. Or is this good enough? Yeah. Which one do you want to see? I don't know which one. Number 2? Number 2. This is good. Number 2 is a good one to look at. Actually, I think that would have been my choice too. And the reason is it's got this summing concept in it, and that's if summation is not on the quiz, then it's certainly going to be on the final. So this concept of summing. So we're going to have something, you know, a sum total which we initialize to 0. We're going to do some logic here. And we're going to add something to sum, and then, you know, at the end we're going to return sum. You know, that's the basic problem here. I'm going to add something together. And you know, like calculating an average or the sum of values in a vector, those are typical problems. But here we're counting the number of occurrences of K. So we could do it like this. Occurrences. We'll just do occurrences. Did I spell that right? CCRR? Is that right? I'm not a good speller. Actually, this, you know, like this. So we're going to have some logic in here, some loop logic, and it's going to so we're going to increment occurrences inside the loop, and then we're going to return the occurrences. How many times does K appear in V? So obviously this, let's go from the inside out. This is going to be, well, we're going to have some index I, and if what's at I happens to be k, then we know we got one. So let's go ahead and add to those increment occurrences. So that's just a matter of making the loop, which is easily done with a for loop. So we'll take I, initialize it to 0. If I is less than v dot size. There we go. So we're going to range I across all the valid indices in V. And for each index I that we look at, we want to see if k is in V of I. If it is, we're going to increment our number of occurrences. And once we're done that loop, we're just going to return the number of occurrences. Now the test code, you got to do test code. Once again, that would be a separate problem. Here we have a boundary case when V is empty. Let's test the boundary case. I had to name occurrences right there all along. What's wrong with my test case? What's wrong with that test case? Huh? No, I want to test the boundary case that V is empty. Huh? It's an integer. We're passing an integer into an assert. We got to pass a bool. We have to use an expression that evaluates to true or false. So what's the expression we need to use there? Someone around? Someone new? Want to get that? What's the test case I'm looking at here? What's wrong with that? With count occurrences returns an int. We can't pass an int into assert. And anyway, what's count occurrences supposed to return in this case? 0. So what does the expression look like that I've highlighted? Nobody? You got to get this. Should equal 0. Count occurrences equal 0. That's it. Okay, so one person. I'm sure half of you are thinking this. I hope. I mean, more than half. All of you. All of you. All of you should be thinking that. Right? Does that make sense? Count occurrences returns an integer. We got to compare it to 0. That's what we think it should be. And this is an expression that evaluates to true or false. In this case, we want an expression that evaluates to true to pass to assert. Let's push back 2. And so now here's our second case. This is not a boundary case, although one value, maybe it's a boundary case. This should also be 0. There's no 3 in there. But if we push back a 3, this should be 1. And we push back another 3, this should be 2. And we push back a 1, and this should remain a 2. So those are good test cases. Yeah.
Would it be better to assert that your variable occurrence equals the 0, 1, 2?
Oh, you mean inside here?
Well, no, outside. I mean, because you're returning that variable occurrences. Shouldn't you be asserting that the variable is actually incremented?
But we don't have access to the variable. Its scope is limited to the inside of the function. So that's a concept of scope. The variable occurrences is being returned here. Actually, what's getting returned is a copy of what's in the memory occurrences. And as soon as we return from the function, the memory that was allocated to store occurrences is no longer valid. It doesn't exist anymore. The function returns a copy of what's in occurrences. And the original storage location that was used for occurrence variable here is now gone. Now that's a concept of scope. So this variable here exists only within the function. Its scope does not, is not outside of the function. Okay, I think that's it then. All right, we'll see you Wednesday.